Hello everyone, I'm Longfei Ying from Imperial College London. Today I'm talking about rate-splitting multiple access for multigroup multicast cellular and satellite communications, physical layer design and link level simulations. Here is the outline. First, I will start from a brief introduction, the background information on rate-splitting multiple access and the motivation of this paper. Then I will introduce the system model, problem formulation, and optimization, RSMA physical layer design for multigroup multicast. Finally, I will show some link level simulation results and the conclusions. RSMA has recently emerged as a powerful non-orthogonal transmission and interference management strategy for multi-antenna wireless networks. It is shown analytically to generalize and encompass four seemingly different strategies, namely orthogonal multiple access, space division multiple access based on linear precoding, power domain non-orthogonal multiple access, and physical layer multicasting. RSMA has been demonstrated to be spectral efficient and energy efficient in a wide range of network loads, user deployments, and CSIT imperfectness. The key behind the flexibility and robust manner of RSMA is to split each message into a common part and a private part. All the common parts are jointly encoded into a common stream to be decoded by all the users, while the private parts are individually encoded into private streams. After the common stream is decoded and subtracted by SIC, each user then decodes its desired private stream and treats the remaining interference as noise. Such framework enables RSMA to partially decode interference and partially treat interference as noise. Most of the existing works on RSMA assume Gaussian impulse and infinite block length. In this work, by leveraging the recent results on the RSMA-based multigroup multicast beamforming with imperfect CSIT, we investigate the design of RSMA physical layer architecture with finite length polar coding, finite alphabet modulation, adaptive modulation and coding algorithm, and SIC receivers, etc. Link level simulations are conducted to show explicit throughput gain of RSMA-based multigroup multicast transmission compared with SDMA-based strategy in both cellular systems and multi-beam satellite systems. In this work, a multigroup multicast downlink system is considered, comprising a transmitter with anti-transmit antennas and K single antenna users. We assume M multicast groups. Distinct contents are simultaneously transmitted to each group. By applying the RSMA strategy, each message intended for group M is split into a common part and a private part. All common parts of the messages are combined and encoded into a common stream as C. The private sub-messages are respectively encoded into S1 to SM. P is the precoding matrix. The transmitted signal contains the precoded common stream and private streams. And by defining mu as mapping a user to its corresponding group, the received signal at user K and the rates of decoding the common and private stream are represented here. When the common stream is decoded, all the private streams are treated as noise, and when we decode the private stream for user K, we treat the other private streams as noise. Imperfect CSIT is considered in this paper. To model the CSIT uncertainty, channel vector H is denoted by the sum of channel estimate and CSIT error. A stochastic average rate framework is adopted. For a given channel estimate, we construct a realization sample These realizations are available at the transmitter and can be used to approximate the average rate through sample average functions. The stochastic average rates are actually short-term measures, which capture the expected performance over CSIT error distribution. RC is the average rate of the common stream, and C1 to Cm are defined as the portions of the common rate at each group. The total average rate of user K is composed of a common rate portion and its private rate. Therefore, we can formulate this optimization problem to maximize the minimum rate amongst all groups, subject to a general transmit power constraint. As we can see, the last constraint is the general transmit power budget, which can transform between a sum power constraint and per antenna power constraints. This non-convex problem can be equivalently transformed into a weighted minimum mean square error problem and solved by alternating optimization. After obtaining the optimized precoders, average rates of the common and private streams will be used to determine appropriate modulation and coding in the AMC algorithm. This figure shows the RSMA transmitter and receiver architecture for multigroup multicast. For the transmitter, we use polar encoding with bit interleaved coded modulation. We also use the optimized precoders and AMC algorithm to determine appropriate modulation and coding scheme. The receiver size include SIC receiver, MMSC equalizer, and demodulation and decoding for polar codes. Polar code is considered in our architecture. The polar encoding operation can be represented in this form. The block length of a polar code is expressed as capital N, and U denotes the uncoded bit vector input to the encoder, which consists of K information bits and N-K frozen bits. The indexes of K information bits are stored in the set A, while the indexes of the frozen bits are stored in the set A complement. To jointly encode the common information bit vectors, all common parts of the group messages WC1 to WCM are at first appended into WC. Then the common uncoded bit vector UC is constructed by placing WC to the information bit indexes. The common coded bit vector is therefore obtained. Similarly, we can construct the private uncoded bit vectors UP1 to UPM by placing the WP1 to WPM to the corresponding information bit indexes. The values of all frozen bits are fixed and known by both encoder and decoder. Bit interleaved coded modulation and AMC algorithm are adopted. The bit vectors are mapped to constellation signals according to gray mapping. The interleaved bit vectors are respectively modulated to a common stream SC and private streams S1 to SM of length S. Appropriate modulation schemes and coding parameters are determined by the AMC algorithm to maximize the system throughput level depending on the channel characteristics. The algorithm uses the average rates RC and R1 to Rm obtained from the formulated optimization problem with imperfect CSIT as link quality metrics. The average rates of the common and private streams are actually calculated based on the optimized precoders by taking an average over 1,000 channel realizations due to the effects of imperfect CSI. According to the given average rate, we at first determine a corresponding modulation scheme from a modulation alphabet set. The set of feasible modulation schemes are calculated based on the average rate and maximum code rate denoted by beta. As a consequence, the modulation alphabet and code rate of each stream can be obtained. Here we demonstrate the performance improvements achieved by RSMA over SDMA for multigroup multicast by link level simulation results. And we compare the obtained throughput levels with the channel bounds. We define throughput as the number of bits which can be transmitted correctly at a single channel use. All maximum fair throughput levels are obtained by averaging over 100 Monte Carlo realizations. Since the instantaneous rate might be different from the calculated average rates due to some unexpected losses, energy backoff needs to be performed. In this figure, we consider a cellular terrestrial multigroup multicast system with 6 users, equally divided into 3 multicast groups. The number of transmit antenna is 6. It can be observed that RSMA has a significant link-level simulation throughput gain over SDMA in the considered imperfect CSIT scenario. The trend of throughput levels is consistent with that of channel bounds. As the CSIT error scaling factor drops from 0.8 to 0.6, the CSIT uncertainty increases, and thus leading to lower throughput results. Then we still consider the system with 6 users and 3 multicast groups and 2 users per group. The number of transmit antenna is 4. So now the system becomes overloaded, or multiplexing gains of SDMA are sacrificed and collapse to 0. The curve of SDMA channel bond gradually saturates as SNR grows. Therefore, the rate gain of RSMA over SDMA is more obvious. By link-level simulations, the maximum fair throughputs of both RSMA and SDMA follow the same trend. The throughput of RSMA outperforms SDMA significantly in the presence of considered imperfect CSIT, namely 0.8 and 0.6. Finally, we consider a multi-beam satellite system where a geostationary satellite equipped with 7 antennas serves 14 single antenna users simultaneously. 2 users are served by each beam, and the system still follows multigroup multicast transmission. This figure shows the channel bounds and throughput versus an increasing per antenna available transmit power. We can still observe the advantage of using RSMA in multi-beam satellite communications over conventional SDMA strategy. In conclusion, this paper investigates the performance of RSMA for multigroup multicast by physical layer design and link-level simulations. The RSMA transmitter and receiver architecture are designed with finite lines polar coding, finite alphabet modulation, adaptive modulation and coding algorithm. Finally, numerical results under imperfect CSIT demonstrate the significant throughput gain achieved by RSMA in both cellular and multi-beam satellite systems. Thank you very much for listening.